Question 12 focuses on pH, pKa, and weak acids and bases in a more conceptual way instead of being purely mathematical. What's sometimes tricky with these is that they do give numbers and people want to plug it into an equation, but it really comes a lot more down to understanding um, equivalence points, half equivalence points, and an acid-base equilibrium than being able to manipulate an equation. So in this one, we've got this, we're kind of calling it the same acid, but here it's labeled as HX6Y. Those were the best graphics I could think about, but we're thinking about them in these two scenarios or in two different concentrations of acid and conjugate base, which could be different points along a titration curve of that. So we could think about I have HA and I'm adding strong base to it. Well, at a certain point I have this, at another point I have that. We want to know about the pH of those based upon the fact that we are given the Ka. And an important part, here's Zoe saying hi, is that when H plus, when the acid component equals the base component, the pH equals the pKa. And in a picture, that would look like our acid that is together is equal to our ion that is by itself. So that's really important to recognize what we have in the pictures. Right there, those are hydroniums, and we often don't show the water molecules in a solution like this. So sometimes what is tempting is to just jump straight to the hydroniums or to think about whether it's an acid or base and compare the pH to 7. But what we need to recognize is that if I had an equal amount of my acid and my conjugate base, then the pH would equal the pKa. So when those are equal, the pH is 5.35. That we know. When it's all acid, it would be lower. When enough of it has been neutralized, that it's all turned into the conjugate base, it would be higher. In my first one here, I've got 1, 2, 3, 4 of it that is still an acid, and only 2 of them have been converted to conjugate base. So the pH is below 5.35. I'm more acidic than basic in terms of that equilibrium. But here I have 1, 2 that are still acids, 1, 2, 3, 4 converted to the conjugate base. So the pH is above 5.35. Remember that 5.35 in this instance would be 3 of these and 3 of those, and that would be the half equivalence point in the titration. This is before the half equivalence point. If we're thinking about a graph, this is after the half equivalence point. And if we were right there at the equivalence point, that's when all of my acid would have converted to its conjugate base. Because it's a weak acid, we would have a weak conjugate base. And kind of like this one, our pH would be above 7. Going on to B, so we'll kind of connect this picture down here, but also this back up to there. What is the Ka value? So I've got the equivalence point, but way more important in lots of these questions is the half equivalence point. That's where we're making that comparison of what do I have more of, and that's where they're equal. So right there, the pH at the half equivalence point is 3. So that means the pKa is 3. And therefore, to undo that log, we do an exponent. Ka is 1 to the negative third. You could get an exact value if we had an exact pH. We could do this in multiple choice, but it's all about understanding that key point. So after 5 milliliters have added, what thing do I have more of? So I'm right here and my pH is very low, but most importantly, I'm before the half equivalence point. Right there, it is all acid. It's all HZ. Right here, HZ equals Z minus. Right here, it has all been converted or reacted to Z minus. So at 5 milliliters, it's before the half equivalence point. So less than half of the HZ has reacted. Therefore, I still have more of my acid than my conjugate base. It would look more like this guy right here. It would still look a lot like this with a little bit that has been converted. This part 3 of B, so 12B3, is probably the question that people get most tripped up on because we're so tied into pH, just meaning that I have either a lot of acid or a lot of base, not thinking of it in terms of solutions and not thinking of it in terms of conjugates, that you can have some conjugate base while still having some acid. So what species is predominant at a pH of 4? So we established before that the half equivalence point was the pH of 3. So pH of 4 is over here somewhere. It's when my I've neutralized a little bit more. And this one's exaggerated how flat it would be. but it would probably be right over here in like the 17 to 18 milliliter range. pH is 4 is after the half equivalence point, and that's what we need to think about. We're before the equivalence point, after the half equivalence point, and what do we know is true about those? Half equivalence point, Hz equals Z minus. Equivalence point, Hz is 0, Z minus is whatever our molarity, or it's the only thing that we have, and we're between those 2 points. So we have more Hz, or excuse me, more Z minus than we have Hz, because we're after the half equivalence point, more than half is reactive. It would be somewhere in this ballpark, and it would look a lot like the HY molecule that we have right there. So it's all about that half equivalence point, them being equal, and that's where we convert or change over which thing do I have more of. So the equivalence point, we're thinking about, well, out of my reactants, out of the acid and conjugate base, or excuse me, the acid and base that I'm reacting, we're kind of changing what's limiting and what's excess. Here at the half equivalence point, we're halfway through the reaction, and that's when half of my acid is turned into its conjugate base. So that's where those two are changing in terms of predominance.